This picture is a recent earthquake we have last year in Chiang Rai. It was a moderate earthquake, but it caused several damage to building and structure in Chiang Rai. So my talk is, as I mentioned, we'll show you several examples of our research activities. But due to the time limit, I may not be able to show all. So these are just a few cases. Let me start from wind engineering. We have a research facility called Warinthchai. This facility we developed together with Thammasat University. So it's a collaboration between two universities to develop this facility. It's the largest wind tunnel we have in Thailand. And this is a picture inside the tunnel. You can see in this tunnel we can simulate the wind flow. It's a uniform type of wind, or it can be the natural turbulence type of wind. And we put a model of our buildings or structure inside this. We can check and identify the wind-induced force or wind-induced effects on the structure. For this example, it is a section of long span bridge. It's called the Rush Mill Bridge in Vietnam. The section bridge, this section model is connected to spring suspension frame outside the tunnel. So the model can move or deflect in vertical and also can twist in the wind. We put this model just to check its aerodynamic stability. If the section is not properly designed, it may develop unstable oscillation. And that's one example of the work we have done. This is a model of billboard structure. The real billboard could be 30 meter high or 50 meter high, but this model is about less than 50 centimeter high. So it's a small model put inside the tunnel that simulates the natural turbulence wind flow. And we can identify the wind load. We put the model on top of a dynamic force sensor. Force sensor allows us to see the wind-induced force, moment, torsion, everything in details. And we can use this for the design of a structure like this. The structure is big in size, and many of them actually were not properly designed, and many of them collapse when it's subject to strong wind. I just heard the recent one I cannot remember the place, but in Thailand, the very large billboard just collapsed, and it's collapsed onto some buildings on truck. This is also another one. The basic problem is when the engineer design this type of structure in the code or in a standard, in many countries they just assume wind effect like a uniform pressure pushing the panel. But in reality it's not like that. In some time instant the pressure may be high on the left, on another instant it will be moved to the right. So it's a dynamic change in the pressure. So this can create the fluctuating load as well as creating a torsion. When the torsion happens, the load on some column may be stronger and some portion of the structure may be much higher than what we expect. So that will lead to unsafe design. So we need to know more about the wind characteristics. Well, this is the size of the model we test. In reality, there are many configurations of the billboard. So we test many of them in our tunnels. So we can learn more about the detailed wind load on this type of structure. This is another example. It's a Buddha statue, standing configuration. The construction has just been completed. It's located in Kanchanaburi province, the western of the Bangkok, about 200 kilometers from here. It's the tallest standing configuration statue. But the model is quite small inside the tunnel, and the shape is quite complex. So you cannot estimate the wind load accurately using any code or standard. This is a very unique picture. So we put it in a wind tunnel, and we can estimate the load. We call the load normal to the face. It's we call drag. The load applied to the side of the statue we call lift. And we can test for different wind attack angle around the building from 0 to 360 degrees. And we have this information provided, given to the structural engineer. And structural engineer can then make a model. Okay, I think many people in this room can make this kind of finite element model. So we can, when we have a detailed structural model combined with accurate wind load, then you can ensure the safety of the building, of this structure. When we apply this, then we can determine how high the stress in each individual element. We can compare with the capacity, and we did that kind of work and identify which elements need to be strengthened, which element is over-designed, and we can determine all this. That is giving you some idea of how the wind load, accurate wind load can help. This is our work many years ago. It's Gramercy resident building. It's a tall building. I understand it's the tallest in Manila, the capital city of Philippines. But you can see that the tall building is surrounded by many other tall buildings. So the effect of the nearby buildings can influence the load on the building that we are interested. Okay, that's a picture of the buildings. I think this is a computer simulated. I should replace it by the real ones. But the idea is when you test this, we can have information to estimate what will be the level of wind-induced vibration on the top floor, whether this will affect, make building occupants feel bad or have a motion sickness or not. We can estimate the wind pressure around the building. That's important and critical information to design the cladding, exterior cladding of the building. We can estimate the structural, the wind load, considering the resonance effect. And we can, account for the effect of nearby buildings. This is important to do wind tunnel tests for tall building. That's an example of the model for pressure measurement. I give you another example. This is a small model of dome structure. The real one is 86 meter span dome, but when you put it to the tunnel, it looks small. And on this dome, we actually drill many holes and connect this to pressure tube, connect the tube to pressure sensor. So we can measure pressure, wind pressure at many locations on the surface of the dome. Yeah, that's a picture of the structure. That's how this looks. It's not working, huh? Okay, I opened the animation separately. You can see this is the picture of pressure. The red or yellow No, the red or orange color means there's an increase in the pressure due to the wind flow. Okay, the wind is coming this way. The green or blue means that there's a reduction in the pressure below atmospheric pressure. So there's kind of what we call this suction effect. So they have an increase in the pressure and reduce in the pressure, creating unsymmetrical load around the dome. And this will create a force effect to the dome truss and dome structure. So in fact, my research team is just conduct wind tunnel test, and we give this information to Dr. Navid's team, ask his team to just carry out analysis. But this is type of information of wind load that structural engineers never had before. But when we use the wind tunnel, then we can have all this data in time domain, in details, applied to our structure, allow us to go into the next stage. I come back. We also carry out, working on the dynamic dampers. I think some of you may have heard about this. This is the tallest steel stack in Thailand. It's located in Rayong. It's about 200 kilometers from here. And on top of this, this type of structure is quite vulnerable to wind effects. If you look at the section of the stack, it's cylindrical, circular section type cylinder. When the wind flow through this section, it will create a vortex, what we call periodic vortex flow around it. And this periodic vortex flow will create periodic change in the pressure around the cylinder, and it creates a kind of excitation force to sway this stack. So our team analyze and calculate what is a possible vibration mode. Mode 1, mode 2. These are two potential vibration modes to be excited by wind. And then we calculate what will be the amplitude of the vibration in mode 1 due to the wind. And this axis shows the wind speed. It says that when the wind speed is high enough, you may have a very large amplitude. But if we install a damper, the amplitude will drop down to very low level. Okay? Because the damper will dissipate energy. That's for second mode. And if we install a damper will bring it down to very safe level of vibration. So that's how we put it. That's the damper. It's made from steel ring and hang it by, the steel rope, wire rope, and connect to viscous damper. This just simple element can be made anywhere, probably except the viscous damper. This we have to purchase from Germany. But the other elements we made it here. So our team designed this damper. We have one damper for first mode. We have another damper for the second mode. That's how it looks during installation. Okay, that's give you some idea. And we are now designing a different type of damper we call liquid damper to be installed in tall buildings. But when the project finishes, I will add more slides to this series. So we are not just doing the research, but we also writing a standard for modern design of wind resistant design for Thailand. I work with my research partner in many other universities to develop this kind of wind design standard. Now I change the subject to earthquake. This shows the tectonic map for this region and the earthquake distribution in this region. One of the research areas that we have been working on is to convert all this earthquake information into seismic hazard map. Okay? That's showing the location of earthquakes and showing the location of active faults. But this information cannot be used directly by engineers, so we have to convert this into ground checking map for engineers to use in the design. So we can make many form of map presenting different index of ground shaking level, and having all these maps, then we can create a new standard. This is a standard, national standard for seismic resistant design of building and structure in Thailand. And we just adopt the US code as a model and adopt our map as a design level, okay? Integrate into this code, so it's become a Thailand specific code. Most of these follow US, except one particular area, the Bangkok zone. This is a very unique zone, which the code in the US cannot help. We have to develop a particular, a new design criteria for this special zone. This is called design spectrum, and design spectrum is quite different from typical design spectrum that you can see in Japanese code, US code, or New Zealand, or many other countries. So this is very unique for Thailand. And this comes from our research on the seismic risk of Bangkok from distant large earthquake. We do not think that earthquake can happen underneath Bangkok. We believe that it can happen in some distance away, like in Kanchanaburi or in Myanmar or in Andaman Sea. But if the magnitude is large enough, the seismic wave from the source can travel to Bangkok and then amplify. It's amplified by the basin in Bangkok. So we need to prepare our buildings for that. Just to understand this problem, we have to look at the case of Mexico. In Mexico in 1985, there was a large earthquake happened, magnitude 8.1. But the location was very far from Mexico City, and many tall buildings collapsed, and more than 10,000 people died because of this earthquake. And if you look at the location of Mexico, Mexico is located here, Mexico City. Earthquake happened here, 400 kilometers away from the city. When we look at the record from seismic station near the source, it shows very strong shaking. That's the signal. When you look at the record, 300 kilometers something from the source, it shows very weak shaking, low level, low intensity. Near the Mexico City, on the rock, show very weak, very low level ground shaking, but on the basin, top, very strong shaking. It's become strong again. Not just strong, but a very low frequency, long period ground motion. So this is very unique type of ground motion we can expect that can be produced by large earthquake at a long distance on top of the basin. So here is Bangkok, the basin in Thailand, and this is a huge basin, the red one, the red zone, because this area in the red zone used to be under the seawater. Now it's exposed to the air. We just starting to move into this area about 4,000 years ago. And now our team together with our research partner work together to identify the dynamic property of the basin. We adopt a technique called array micro tremor. Of course, the technique is developed in Japan, but now it's used in many countries around the world to identify important property of the basin. That's how we apply. We start with a small array, then getting larger and larger. When array become about 1 kilometer in size, we can identify the dynamic property down to 1 kilometer in depth. So by this way, we can easily check the dynamic property of the basin at many points. At the moment, we have conducted this type of test more than 100 locations in this Bangkok basin. So we have enough information to model the basin property. That's type of information. So we are going to use this information to create a model for the basin again, and then develop a new design spectrum for Bangkok in the future. It will come out very soon, maybe in one year or 1 or 2 years. So in parallel to the checking of the basin property, we have to check also the dynamic property of our tall buildings. So that's information about vibration mode of tall buildings, first mode, second mode. Okay. So our team together with our partner have checked vibration property of more than 100 buildings in Bangkok and in Chiang Mai and in many areas. So now we have very high quality information about dynamic property of the structure in Thailand. Based on this, we 2-3 years ago, we have conducted kind of using all this information to estimate what could be the impact by such a large earthquake at long distance from Bangkok. What could be the possible impact to this capital city? So our team have collected more than drawings of 200 buildings, existing buildings in Bangkok. We have made a model of around 100 buildings, detailed computer model. That's an example. This building, when subject to a rare but strong shaking coming from long distance earthquake, what will be the impact? We found that out of 1,400 tall buildings in Bangkok, maybe not many, maybe less than 20 buildings will suffer severe damage up to the level that it can collapse. Okay, I think less than 20, but 20 is quite already high number. But the majority, like several hundreds, may suffer damage to non-structural components. And we recently estimate how much it will, how long it will take to repair this. It seems it will take maybe around half year or 1 year. So you may not be able to use the buildings for about 1 year after the earthquake. That could produce a very high economic impact and social impact to the capital city. Okay, what else? That's a numerical analysis, but parallel to this, in our lab, we have conducted several tests of structural element. This is example for column, but not designed for earthquake, because most buildings here are not designed for earthquake. So we test how it will perform when it's subject to strong earthquake. That's the model of slab column connection. Because the slab column frame is quite popular here in this country, also in many countries in Asia. So this slab column connection is a critical connection. If it fails, it may trigger the what you call punching shear failure and trigger progressive collapse of the structure. We also test the frame with infill wall, brick wall, to understand the interaction between structural component and non-structural wall. And some of our work on bucking restraint brace. This is one of the techniques to improve the performance. In Japan, they call this metallic damper. It's a metal frame that can help dissipate energy. Okay, metal brace. And this is probably the last one, and I think Dr. Panche will explain more into this. This is our work on the precast system. Okay, I think recently precast concrete structures now is becoming more and more popular. But the precast structure, if it's not properly designed, it can be very vulnerable to ground shaking. And in our team is trying to check a new idea of precast system. The new idea is the wall is precast, beam is precast, columns are precast, and they are, all their connection are allowed to open and close and be able to close down. Okay? They are not rigidly connected to each other, but they allow all the elements to move, to open and close. Let me show you by showing the test. You can see the wall under when we apply the load. The wall just rock. This note that is not fixed to the base. It can lift up on one side, but it will come back, return. Some people may feel that this is a weak structure, but in fact, it makes the rocking allow the structure to become very, it have a very high resistance to ground shaking because it have a high deformation ability. If you look again, the connection between the beams and wall, beams to column, it can open and close. So by this way, there will be not much damage to elements. But this is a new idea, which now in many countries is a kind of a hot research topic issue, and maybe becoming the future for precast system. So I'd like to end my talk, and we'll be glad to answer any question. Thank you.
Concerning your acceleration spectrum,
Yes.
in Thailand.
Okay. Yes.
What is the shape of the spectrum there?
Yeah.
Do you have any certain reason?
This one, right?
Yes, this one.
Yeah. For other location in Thailand, is normal shape. It will have high spectral acceleration in very short period, 0.1, 0.2, 0.3, and then spectral acceleration will come down as period increase. But this one, the peak will be at about 2 seconds. Okay, that is kind of because there's no earthquake underneath the basin. Earthquake will come from the distance about 200 kilometers or more from a large earthquake. Okay? When we talk about a large distant earthquake, high frequency component will be filtered out. It will attenuate down. Only long period around that range will be able to reach Bangkok. And then that period will be amplified further by the basin, because the basin have ability to amplify the ground shaking around 1 to 4 seconds. So that's all together. Come out, produce this shape.
I can see that certain number of your vertical axis is, what is the maximum acceleration?
Not very high. It's about this 0.2 G, 0.3 G.
0.3, okay.
Yeah. But 0.2 G at the period of 2 seconds can be very high. Yes, that can be strong. Okay? And then we have acceleration recorder located in Bangkok Basin. And we have record the ground shaking from many earthquakes in the past 10 years. And it turned out to be, the shape looks like this. The shape doesn't look like a typical spectrum. The shape shows very high peak and long period. Okay, so it's confirmed by the real measurement.
Do you think you needed more reinforcement for your building after you use this acceleration spectrum?
Well, we think that tall buildings need to be carefully designed, but low-rise building will not be so much affected by this type of earthquake. Okay, tall buildings will be more.
Okay, for new one, it's okay because you can design for that. But existing building, what you can do?
Existing building we have checked, and we found that some, but very few, may be at risk. Most of them are designed for some level of wind load that provide them some level of lateral strength. But there's a big variation in existing building, particularly those with low number of shear wall. So those may be at higher risk. And in fact, we propose to Bangkok Metropolitan Administration that we can even identify which building are at risk. But will they be able to check, to do something? That's another story. It's not difficult for our team to check and identify, but what to do after that will be difficult.
Thank you.
On the wind load tunnel test, can you give us the commercial value of that?
Commercial value.
Commercial cost?
The cost?
Yes. How can we estimate the cost of testing the model in the tunnel?
Actually, it's not a good idea to give a package here in front of everyone.
Okay.
But I can give you some rough idea.
Right.
If you have a very tall building, one tower, and you want to check wind load, you want to check pressure, and you want to check the wind effect to pedestrian around the pedestrian level. These are called 3 components in a package. This is a cost around 1 million baht, approximately, in our package. But if you do only load, structure, wind load, it will be about 0.4 or 0.3 million. Pressure will be about 0.4 to 0.5. That's around the rough figure.
But if we have to build the model of the building around...
This package includes making a model as well.
I see.
Yeah.
What is the scale of the model, and also the scale material that we represented in the model?
The scale is about 1 to 300. 300 down, reduced to 1, or 400 to 1, approximately. The material used is different. If you want to check the wind load, we may have to make a model very light. Okay? If we want to measure the pressure, we have to make the model very rigid. So for pressure, we may use acrylic, so that we can see the wind, the pressure pipe and everything. But for wind load, we use balsa wood with aluminum frame inside. Yeah, that's a rough idea.
Thank you.
For the national standard, DPT 1302,
Yes.
the last one, they're still able to use and safety.
You mean this one?
Yes.
So we are now revising this standard. But if you the new version will come out soon in 1 or 2 years. Okay? At the moment you can use it. The problem is if you use it to design tall buildings,
Yeah.
most engineers will use a procedure called response spectrum analysis.
Yes.
Our team found that response spectrum analysis procedure is not a good procedure. So we recommend not to use them.
Wow. What I can do now?
In the new procedure, we will propose a new version.
When?
It's in 1 or 2 years, but at the moment there are other more difficult approach. We call time history analysis approach, but many engineers here can do it. But if that may require more detailed discussion. But we are willing to advise. Yeah.
Should I stop to work now?
No. That's a way to do it in to handle this problem.
But can you distribute the draft first? For we know something very good for the future. Draft version.
The draft version will come out very soon because we have to go for technical hearing. Technical hearing will be organized in a few months' time.
How much percent for increase the reinforcement? Maybe we can do.
No, I think if you have enough number of shear wall, you may not have to increase the amount of reinforcement. Okay. Sometimes if you increase amount of vertical reinforcement in the wall too much, you have to increase also the shear reinforcement in proportion. So more is not good, not always a good idea. Sometimes you need less.
They not allow us to do that.
Huh?
Architect design, they're not allowed us to do that sometimes.
To do what?
Maybe a lot of shear wall and something like that.
I think I'm also talking with architect team, group. Association of Architects in Thailand, they are quite active right after Chiang Rai earthquake. And now they are trying to develop the first design guideline for architects for seismic design. So I think the climate is changing now. They may pay more attention to this issue in the future.
Thank you.
Is there any other question?
What about for medium-rise buildings in Bangkok due to long-distance earthquake? What would be the effect?
We think that although we check roughly, I think low-rise 2, 3, up to maybe 6, 7 story, or even up to 10, may not have any major effect from this distant earthquake. Okay, but a taller one, like a 15 story, 20 story, 30, 40, will be in a range that is natural period, is in a range that can be excited by the ground shaking. But the law requires that all the buildings above 15 meters have to be designed for earthquake resistance. Okay, this says that Dr. Navid is not around, so let me close my talk and invite Dr. Panjet to continue.